Okay, I think we will get started. So, we were starting to look at power okay, in electromagnetic fields, and we just briefly opened up the calculation of power. I think we will be expanding on that in this lecture. So, towards the end of the previous lecture, we just wrote down that E cross H is equal to P, or the unit of electric field is in volts per meter, and the unit of magnetic field is in amperes per meter, and the unit of the right hand side quantity, all right, is volt ampere per meter square. Okay. But if the phase difference between the electric and the magnetic field is 0, you could always write this down as watts per meter square. So, instead of calling it power, it is more appropriate to call this as power density. Okay. It gives you a notion about how concentrated the power is with respect to a given area, right. So, it is power density. Okay. Since we already saw that the unit of electric field is in volt per meter and magnetic field is in ampere per meter, the right hand side has to be equal to volt ampere per meter square, all right. And only when the phase difference between electric and magnetic fields is 0, this becomes watts per square meter, all right. So, in generic sense, the right hand side represents a quantity similar to apparent power in electric circuits, where you had the unit to be volt amperes. Okay. So, in the case of electric power, you would have talked about apparent power, active power and reactive power, all right. So, this right hand side equivalently is generally apparent power in electric circuits. Okay. Okay. Now, the given an area, right, one can calculate the net outward power, all right. The net outward power is usually given by this variable W. Okay. So, it is the closed integral of power density over the given area, all right. That is the net outward power. Suppose you were to calculate the intensity of a electromagnetic beam that is hitting a surface, you will take the power density at every place, integrate it over the area. Okay. That is the net power that is delivered. Okay. Okay. Now, let us start to look at this in a little bit more detail, because we already know that the electric field that we are considering now is a time harmonic quantity for this portions of the lecture, and the magnetic field is also time harmonic. So, what is the effect of time on the power that is passing through a unit area is first that we need to understand. Okay. So, for this, let us go ahead and make the expressions for the electric and the magnetic fields clear with respect to the spatial and temporal variable, and then write down the power, and then let us start looking at the power. What kinds of power are there other than apparent, real and reactive power, all right, and which power should we analyze, which power should we not analyze, which power gives you meaningful conclusions, which of them does not give you meaningful conclusions, all right, always, etc. Right. So, these are the things that we need to see. So, for this we start to look at instantaneous electric and magnetic fields. Okay. Okay. By instantaneous, I mean that I will be using e to the j omega t for describing both the electric and the magnetic field. It has the effect of time, alright. So, I am using e to the j omega t to describe electric and magnetic fields as we had seen before, right. The beginning when we had started with AC, alright, electromagnetic fields. So, we had included the periodicity with respect to time to be an exponential, and then we will take the real part of this exponential, right. So, when we talk about instantaneous, this means that you are going to be writing down the electric field which is a function of position x, y, z and time. So, 3 space variables and 1 time variable, right, and we are simply writing this down as real part of E naught, which is a function of x, y, z spatial variables, right, and I am also including the effect of time where it is periodic with respect to time. Okay. Okay, this is what we mean by instantaneous field, and in this case I have taken a very generic scenario where the electric field is a function of x, y and z. Okay. Similarly, the magnetic field can also be written as h naught, which is a function of space, periodic with time. Okay. This is a starting point for the analysis, but we can make this even more generic. Right now, we have included all the space variables and the time variable. We can also make it a little bit more generic. The little bit more generic part comes from including the phase difference between E and H. Okay. So, it is possible for you to have a phase difference between E and H, all right. So, we can now take a case where we would say that right. So, I will say that the electric field with respect to a reference has a phase phi e, okay, and the unit vector is given by E hat. Okay. Similarly, for the case of the magnetic field, the most generic case with respect to a reference, okay, it has a phase phi h and the unit vector describing the magnetic field is given by h hat. This becomes a very generic expression for electric and magnetic fields. Okay. So, it includes the position, it includes the time, it also includes some phase with respect to a reference for electric and magnetic fields. Okay. It is quite possible that you choose the reference in such a way that phi e is equal to 0, and then say with respect to the reference, same reference, what is the value of phi h, and that way you will be able to eliminate one of these two variables, right. But in the most generic case, with respect to a reference, it is completely okay for electric field to have a phase. With respect to the same reference, magnetic field has some other phase. That means that the electric and the magnetic fields could have a phase difference between them in the most generic case. Okay. So, now since we are talking about the real part of these exponentials, okay, we could always say that the electric field, right, is going to look like some value E naught at some position x, y, z. Okay. Since we are taking the real part, we can directly go ahead and say that it looks like a cosine it looks like a cosine. Phi e plus omega t is the net phase or it is the total phase, okay, and it points in the direction E hat. Okay. One could always orient the coordinate axis in such a way that E hat is pointing to one of the Cartesian coordinates, say x, y or z depending upon the problem. Similarly, the magnetic field can also be written as h naught of x, y, z cosine phi h plus omega t h hat. Okay. Now, since we are dealing with time also, okay, so we have included the effect of time also, and we know that this function is periodic with respect to time. Okay. If you were to calculate the power density directly by using E cross H is equal to P, our understanding is that that is also going to depend on time. Okay. So, let us first start with the simple calculation for power density, all right, and since this is instantaneous electric field and instantaneous magnetic field that we are using, the power that we are calculating will be known as instantaneous power, all right, or instantaneous power density, you used to call it. Okay. So, okay. Okay. And we have already written down the expression for the electric and the magnetic field. So, we just substitute the cosines that we have just written. We have written E naught cosine omega E plus omega t plus phi E, right. Similarly, we have written an expression for the magnetic field with the real part, right. So, we just substitute that and we get E naught H naught cosine omega t plus phi E, that is coming from the electric field expression, and we have cosine omega t plus phi h coming from the magnetic field expression, and we have a cross product on the right hand side, which is a vector operation. So, you have to take the unit vector for electric and magnetic fields and cross them, so that your right hand rule is going to be preserved, right. Okay. Now that we have written an expression which is a product of two cosines, you can always use some trigonometric identity and convert this to a sum of cosines. Okay. So, we could write this down as E naught H naught divided by 2 multiplied by, you can take the difference between the two. So, you will have omega t plus phi E minus omega t plus phi h, all right. So, you will be having the first term to look like cos phi E minus phi h, right, plus you can take the sum of the two arguments of the cosine. So, you will be having cos 2 omega t plus phi E plus phi h okay. So, all we have done is we have taken the electric and the magnetic field expressions and merely substituted them in the power expression that we had started with, all right. And this quantity, if you look at it on the right hand side, right, it depends on time. Okay. So, this quantity is known as instantaneous power or instantaneous power density. Now, the question that one can ask is, what is the relationship between the instantaneous power and the time, all right. It is very clear that you have a cosine 2 omega t plus something, all right, means that it is a periodic power, instantaneous power density also, all right, which means that we have some possibilities over here. We know that the cosine can be positive, cosine can be negative, or the cosine can be 0. It could also be in such a way that it exactly balances this quantity, all right, when it is negative and the entire term becomes 0 at some instant of time, the entire term is positive at some other instance of time, and the entire thing is negative at some other instance of time. So, instantaneous power with respect to time, you will see that the vector is pointing in very different ways, all right. So, you may either have a positive quantity or 0 or negative quantity, okay, which means that to make some meaningful conclusions it's not easy to do it with instantaneous power, okay, because instantaneous power at some instant of time can be 0. You cannot draw a conclusion that there is no power that is passing through the given area, right. Same way you can have instantaneous power to be positive, which is fine for you to draw some conclusions normally, but in some other instance of time you will have negative, right. So, this is not an easy quantity to interpret to make physical inferences, okay. So, it is not the best quantity for making physical inferences, because it can be positive, negative or 0. So, to just write this down, right, clearly, right. Okay. Instantaneous power could be positive, negative or 0, which means that drawing conclusions is not easy. Okay. Okay. Then what other option do we have? Now, one of the things that we look at is the right hand side is depending upon time. At some instant of time you are having positive power, at some other instant of time you could have negative power, at another instant of time you could have 0 power, etc. Which means that we need to look at a quantity that is not dependent on time to make some meaningful analysis, all right. And that quantity is known as average power density, which is similar to your electric circuits, okay. So, you will be having average power in your electric circuits. So, similarly you are having average power density over here. Okay. So, the way the average power is defined is over a time period, okay. You are going to integrate your instantaneous power, okay. Now, this could be the time period of E, this could be the time period of H, both of them are going to be at the same frequency. So, it is perfectly fine to take the time period of E or H, all right, which means that you are going to be looking at substituting the value of instantaneous power in this expression. And one of the things that we can immediately notice is the instantaneous power broadly can be split into two quantities, E naught H naught divided by 2 cos phi E minus phi H E cross H, that is one term. The other term is E naught H naught divided by 2 cos 2 omega t plus phi E plus phi H E cross H. So, one term, and the second term is dependent upon time, and it is dependent upon time in a periodic manner, and the function being precisely a cosine, right. So, the first term, yes, we can understand that it is seems to be independent of time. So, if I integrate it, I will just have to multiply it with the time period in this case, and then I have a 1 by t coming out. So, the time and time gets cancelled. So, the first term remains as such in the case of average power density. In the case of second term, when you integrate the cosine over an entire time period, you will end up getting a 0, all right. So, what that means is you are removing that quantity from the picture completely, and then what you are left with is something that is not dependent on the current value of time, and that is average power density, and that should give you a valid quantity to make some conclusions on, okay. So, I will write down the expression. So, this is 1 by t integral p dt, right. So, this can also be written as half real part of E naught j phi E naught j omega t E hat crossed with h naught e to the j phi h e to the j omega t h hat. Or I mean, you could also write this down as the expression that we just now got. You can just say that this is half E naught h naught cos phi e minus phi h that is also fine. Okay. Now, if you look at the first expression that I have written, all right, there is a small problem with that expression. Okay, there is a small problem, right? This expression. This expression is what we already got, so we cannot doubt that. All right. Now, one of the things I notice here is that if I take this cross product, I will never get phi e minus phi h, all right. So, which tells you that there is something else going on. So, here I have the expression for the average power to be half E naught h naught cos phi e minus phi h E cross h. So, I just cannot simply write this as half real part of E vector crossed with h vector, because that will never give me phi e minus phi h, it will only give me phi e plus phi h, which is not consistent with the derivation I just made. All right, which means that we need to make some adjustment to one of these quantities. All right, the phase is not being calculated correctly. So, the only way to get phi e minus phi h is to tweak the phase of your magnetic field in the expression. Right. So, the correct way to write this down is by actually saying it is minus j phi h and minus j omega t h hat. Okay. Otherwise, you will not end up with this expression. Remember that we are trying to write this expression, all right, using the exponentials, that is all right. And when we are doing that, we have to take into account the phase accurately, right. So, the only way you will be able to get it is this, which just means that we could always write down the average power to look like complement, okay, of h. So, E cross h complement is the correct way to write the actual power. So, the complement there comes because you have a phase difference between E and h, phi E minus phi h. To account for that phase difference, the way to calculate power is to take E cross h complement. Many of you may remember in low frequency circuit, you would have had Vi complement in AC circuits power calculation. You would have had half Vi complement to be the average power in AC circuits, right. This is exactly a similar case, all right, where to account for the phase difference between E and H, you have to take the complement of H. Okay. Now, since this quantity is independent of time, okay, it gives you some meaningful quantity to make actual conclusions. Okay. It gives you whether there is an average power flow or not, whether there is an average power flow into the surface or out of the surface or not, all right. So, this is a quantity that you can use to make some meaningful conclusions, and what kind of meaningful conclusions can one make, whether is it a source, is it a detector, all right. So, things like that, or whether it is passing through a surface or not, all right. So, you may have inward power being equal to the outward power on the other side, etc. So, the average power is the quantity that you need to look into. Okay. The other thing that we are looking at is the power is dependent upon E cross H complement. Now, whenever we have something like this E cross H complement, all right, and if we write down only the real part, you will get cos of phi E minus phi H, all right. This means that if you have a configuration where the electric and the magnetic field unit vectors are perpendicular to each other following a right hand rule. So, direction of propagation is say your thumb, all right, electric and magnetic fields are given by your index and the middle fingers, okay. It forms a perfect right handed configuration for your plane wave to travel. but we still are not talking about the phase when we are talking about the right hand rule. We are just talking about the unit vectors, we are not talking about the phase. When we look at phi e minus phi h, it tells you something about the phase. Okay? So, it means that you can have a perfect right handed configuration, electric magnetic fields and your Poynting vector say is perfectly defined according to the directions of your fingers. But it is quite possible that the electric and the magnetic fields are 90 degrees out of phase. It is possible, it still forms a right handed configuration and it still seems to be a valid solution for your Poynting vector, alright. If that happens, you do not get any power. Okay. If your electric field and magnetic field are in quadrature phase, okay. Quadrature phase means 1/4 of your wavelength, alright. So, it is pi by 2, okay. Then you may not get any power transfer at all. It is very similar to the case where you have passive components in electric circuits which are L and C. Okay. In resistor, we will say that the current and the voltage are in phase and the power will simply be V times I, and if you want to be very specific, you can say V times I cos phi, where cos phi is your power factor, alright, or phi is the phase difference between your current and voltage. Because phi is equal to 0 degrees, you will substitute cos phi as 1 and then you will get it to be Vi watts. In the case of pure inductor, we know that V is equal to L di dt, alright, which means that you will be having voltage and current out of phase by 90 degrees. More specifically, you will say that the current lags the voltage by 90 degrees in phase, and then when you take Vi cos phi, you will get 0. That means that your inductor cannot consume any power. There will not be a power transfer to a pure inductor. Same way in a capacitor, you will be having C dV dt to be your I, which means that your voltage and current are going to be out of phase by 90 degrees, or current will lead the voltage by 90 degrees. Again, you cannot transfer power to capacitor. All power, power cannot be dissipated by the capacitor, alright. So, the equivalent can happen here also, alright. You can have media in which the electric and the magnetic fields will not have any phase difference between each other. You can have some other media where maybe the electric and the magnetic fields have some phase difference between each other. The phase difference can be positive, phase difference can be negative, phase difference can be 0 depending upon the choice of the medium. And in the most general case, half real E cross H complement should give you an idea about all that. Okay. So, most of the cases are very similar to your electric circuits, and that is something to bear in mind. Okay. And one of the conclusions that one can draw from this is not all electromagnetic fields carry power. It is completely possible to describe an electromagnetic field with an electric magnetic field component perfectly aligned to your right hand coordinate system, alright, but still have a relative phase difference between the electric and the magnetic field to be 90 degrees, and that electromagnetic wave does not carry any power at all. Okay. So, not all electromagnetic fields can carry power. So, this is one thing to remember, right. So, for you to effectively deliver power from one side to the other, the phase difference between E and H is very important. Okay. The other conclusion that you can also draw from this is that the electric and the magnetic fields do not cross each other, right. That is a subtle difference that we will see when we do a computational simulation of the electric and the magnetic fields in the EM field, right. Now that some idea about the power should be there and some analogy between low frequency circuits and plane wave electromagnetics should be there, alright, we can go to some more generic cases, right. A more generic case is where we are talking about a plane wave traveling in arbitrary direction. So, here we are already talking about plane wave being a function of x, y, z time, and we have marked the direction of the plane wave to be say Ex for electric field, alright, Eh for the magnetic field, Ex cross Eh for the Poynting vector, alright. We have already made it generic enough, but we can also make it even more generic by looking at how do we describe electromagnetic fields traveling in arbitrary directions in the form of plane waves? Okay. Now, I will just describe what I am trying to do, right. Let us say that okay, many times in problems you will be given something like it is traveling in a direction, alright, it hits some medium, try to calculate reflection and transmission coefficients, and then you may be asked to figure out what is the power transferred, etc. In those cases, first you should be able to write down the expression for the plane wave traveling in an arbitrary direction, then only you can do cross product, dot product, etc. accurately, otherwise you will not be able to do it. So, we need to know how to describe a plane wave traveling in an arbitrary direction with respect to a fixed coordinate axis. Okay. So, let us say that this arbitrary direction that we are talking about, right, has a unit vector n hat, okay, and this n hat is making an angle phi x with respect to x axis, phi y with respect to y axis, please remember that previously when we were talking about plane wave, we made it very convenient in such a way that the direction of propagation was assumed to be z, you just assume the E field to be x oriented and magnetic field to be y oriented, alright. So, it was very easy, you had very few unit vectors in different directions to manipulate, but it is also possible that the coordinate axis is fixed, alright, and a plane wave is allowed to travel, you should be able to describe that also. In practice, it is a good approach to do either one, you can always orient your thumb to the direction pointing, to the direction of the travel and say that is going to be my z axis. In that case, you are defining a coordinate axis for the problem. The opposite can also be fine, if you are comfortable with having fixed coordinate axis and then describing what a plane wave is doing, that is also fine, alright. Depends upon what the student finds more comfortable, right. Most of the times I find it comfortable to orient my thumb to the z axis, right. That way it becomes easy for me to describe the fields, but this is also a valid thing, right. Okay. So, let us draw a diagram, okay, and let us mark our coordinate axis, right. Say I am having x, x, y and z, okay. And it is going to be tough for me to draw in 3D, okay. So, you have to make some imagination, right. So, I am having a direction of travel, say something like this, okay. I am calling the unit vector to be n hat. So, the angle it makes with respect to the x axis, I will call that as phi x. The angle it makes with respect to the y axis is phi y, right. With respect to the z axis, say phi z. Okay. And I will mark the origin, say with some letter O. Okay. Now, we can also be a little bit more clear about what is happening here. We can always draw a plane of constant phase. Okay. This is a plane wave, it is traveling in a direction. In the plane perpendicular to it, it is a constant phase plane. All the electric field is having the constant phase, it has the same phase. Only when it moves to another place at another instant of time, the phase has changed. Okay. So, this aspect where we are drawing something like this, right, it's a plane of constant phase. Okay. And let us say that this point is A. So, now we have a unit vector, the direction of propagation to be n hat. Okay. Coordinate axis defined according to the right hand system x, y, z should form a perfect right hand triad, all right. Angle between the x, y, z are defined, and we have drawn a plane which is describing a constant phase plane at the point A, that is here, that is the setup that we are having. Now, we can also have another point on this plane, okay, and that plane would have the same phase as the wave at point A, all right. That is why it is a plane of constant phase, okay. So, you can always have another point and call it P, okay. Even though you have marked a different point, the wave that is traveling in this plane at that plane at all the points has the same phase, okay. Remember that when we were orienting our direction of propagation n hat to be in z direction, we wrote down the equation to be cos omega t minus beta z, okay. So, cos omega t minus beta z means that in x and y directions the plane is infinitely large. Wherever you take a point on that plane, the description of the field is cos omega t minus beta z, right. So, you could draw a large plane, and if you take the point P, it is lying on the same face, okay. But the way we have drawn a coordinate system over here, it is perfectly possible for me to draw a vector from point O or the origin going to this point P, but it will not look like n hat, okay. It is the way we have defined the coordinate system. You could always draw a different vector, okay. We have defined an origin to be a point, and we are taking a plane of constant phase. It is already understood that I can draw a vector going straight to the center of this plane, all right, and hitting the plane at 90 degrees. I could also draw another vector going from the origin say to the edge of the plane, but it is not hitting the plane at 90 degrees, all right. But given the coordinate system, if I have to describe that point on the plane, that is what I have to use, all right. So, it is perfectly possible for us to have points on this plane, all right, and you could connect it to the origin using different vectors, right. So, this makes it a little bit tedious to describe a plane wave, all right, in this kind of a scenario where it is traveling in an arbitrary direction. It is a plane wave, that means it has a large plane where the phase is constant, but you have a coordinate axis with a fixed origin, and you have to describe at every point on this plane the phase has to be constant, right. So, it becomes a little bit more challenging to think about it, but once you look at this problem and orient everything to a coordinate axis, then it becomes very simple, right. But in an arbitrary direction, it is always a little bit more complicated, okay. So, let us give some mathematical descriptions to the quantities that we have written, okay. N hat is the unit vector, we know how to write that, okay. So, we can write this as cosine phi x x hat plus cosine phi y y hat plus cosine phi z z hat, okay. So, this is the unit vector, okay, n, which describes the direction of propagation. So, the next phase front will be a space, what to say, it's a version which has travelled further or ahead, etc. So, if you assume the direction is like this, then the next plane that you would draw will be on the unit vector passing exactly perpendicular to this plane again, all right. So, we have drawn cos phi x x hat, cos phi y y hat, cos phi z hat. This is the expression for the unit vector. This is how you will be writing the expression for the unit vector. The position which we have just discussed, okay, that is the point P, is described by vector r. Okay. And whenever you have a vector that you have to describe, all right, in this kind of a scenario, all you would just do is you will just write this down as x, y, z coordinates of that particular point. So, you can always say that the r vector which describes the position which you want to consider, okay, is simply going to be given by x units in x direction, y units in y direction, z units in z direction. This is the only way we can describe, right. Now, the objective of this exercise is to write down the electric field expression, is to write down the magnetic field expression. Once you have that, you can find out the power, etc. Okay. Now, before going into more details, n describes the direction of travel of your wave. That should be very clear now, all right. But we already have talked about E, H and K, all right. K describes the direction of your Poynting vector or direction of power transfer, okay. So, which means that K should be some multiple of n, or K could be equal to n also, but the direction of K should be direction of n, all right. So, that should be clear. So, let us make that clear in a little bit more sensible manner. The relationship between K and n is just multiplying with a constant beta, right, and beta is given by 2 pi over lambda, where lambda is the wavelength in the medium that you are considering. Remember that we have talked about the coordinates, we have not described the medium. The medium could be air, the medium could be water, the medium could be slightly conductive, or it could be a poor dielectric, etc. In any of these media, in the previous classes we have seen that beta could be different. We also saw that as omega increases, alpha could be different, beta could be different, all right, etc. So, beta multiplied by n hat, which means that the expression for k vector, okay, is beta cos phi x x hat plus beta cos phi y y hat plus beta cos phi z z hat. Okay. Now, we also have to remember that when we are doing this, the immediate thing that should come to our mind is we are talking about a plane wave. E dot k is 0, that means the dot product between the electric field and the Poynting vector is 0. That means the projection of electric field on the Poynting vector or the projection of Poynting vector on the electric field vector is 0. Okay. They are orthogonal to each other. If you take a projection of this on this, you will get nothing, right. Okay. You can also write this down as previously we had. This means that we are talking about a transverse electromagnetic wave, okay, and we are also talking specifically about plane waves in this case. Okay. Now, to just make you feel comfortable with the way we have written the k, we can always think of the problem in the past that we have done, all right. We always said that let us assume that the direction of travel is z. This was our most go to Cartesian coordinate system. Direction of travel is z. Suppose direction of travel is z, all right. One can ask, what is k, right. So, let us look at k for a okay. How do we write this? Okay. So, let us look at the expression beta cos phi x x hat. So, I will be taking beta outside, it is just a constant, cos phi x x hat plus cos phi y y hat plus cos phi z z hat. For a z directed wave, all right, the way you will draw the unit vector n hat is along the z axis. That is it. So, in the direction, I mean in the diagram that we had before, this n hat will be along z axis, it will be going up, all right. So, it will be starting here, it will be going there. Phi x will become 90 degrees, phi y will become 90 degrees because it is the angle measured from the x axis to the vector, all right. So, phi x will become 90 degrees, phi y will also become 90 degrees, which means that you will be writing this as beta times cos pi by 2 x hat plus cos pi by 2 y hat plus cos phi z z hat. Now, since it is along the z direction, phi z is going to be 0 degrees, all right. So, you can just scratch that phi z over there and just write as 0 degrees or 0 radians, right. So, this means that I will end up with an expression that just says beta times z hat. Okay. This is the first step, is to be able to write down k vector for something which is given to you for an electromagnetic wave. It is traveling in some direction. How do you write down the k vector? This is the first step. Okay. So, in a generic case, you should be able to take a coordinate system, draw the direction of travel, mark the unit vector, multiply that unit vector with beta in that medium, then measure the angles from the x, y and z axis, write down cos phi x, cos phi y, cos phi z, write down k vector. This is the first step, okay. And then there is only a couple more steps, I will describe that in next class, okay. And once you are done with that, you know how to write a plane wave when you are given a coordinate system and arbitrary direction of travel. Once you know that, things are very simple, you can always orient it in the way you want and you can start writing down things. In many practical problems, if you orient the coordinate axis to suit one part of your analysis, the other part may not be exactly in a convenient location. For example, if you have a transmitter that is located at 0 0 0, all right, and you say that it is giving something in x, I mean in z direction, etc., you may have some medium which reflects it at say 45 degrees. All right, and it goes to another place, you want to describe that, and then you do a series of manipulations and then you have a detector that is finally placed in some other direction. You do not want to rotate the coordinate system for every component in your analysis, you want to keep it fixed and then see what happens, it will help you in those kinds of scenarios, okay. But the first step is to identify k vector, all right. K vector is beta times whatever your unit vector is to the direction which is normal to the surface, okay. You cannot take point P in our diagram, you have to take point A, all right, for defining your k. This is the first step. The remaining steps are very simple, we will go over it in the next class, and in the next class you should be comfortable writing down plane wave in an arbitrary direction. Once we are done with that, then the scope for dealing with interfaces comes into the picture. We can deal with arbitrary directed waves hitting some reflecting medium, refraction, all these things can come into the picture. So, that is the idea, right. So, I will stop here, we will meet in the next class.